All right, in this video, we're going to look at the lesson 2.9 to figure out continuous versus discontinuous at specific points. But to start it, we're going to first define what it means to be continuous for functions. And we're going to do that by doing the opposite. We're going to examine the idea of discontinuous first. Very simple definition is when I'm drawing a graph, if I have to lift up my pencil to finish the graph, which I have to here lift up my pen to come to the other side, we call it discontinuous. It's the same over here with this jump discontinuity. As I draw from left to right and from left to right, I go through, when I hit this open circle right here, I have to jump down here in order to finish. So I had to lift up my pen. Even for this whole graph, as I go from left to right, once I hit that hole, I can't go through it. I have to lift up my pen, jump over it, and then draw again. So that's what it means for a function to be discontinuous. The idea of you have to be able to go from left to right while sketching it without lifting up your pen. There's no breaks in the graph. And that's going to help us examine what it means for a point to be discontinuous for a function. And so as I look at these graphs are discontinuous. And I can tell because in this first graph, it was discontinuous right here, right at that vertical asymptote. And that vertical asymptote was x equals 0. Everywhere else on that function, everywhere else, there's a point, there's a point, there's a point. I can draw, 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 except for right there. Right there, I couldn't draw. And so I have my point, my point, my point, my point, my point, my point, and then just at that 0, I had to lift up my pen. But everywhere else, I could just keep drawing. And the same goes for here. The only place I had to lift up my pen was where I had this hole at x equals 0 for both functions. But all of the other points, all the other x values, I can draw through. I can create my curve for each one. And the same with the last one. I can draw from left to right until I hit that hole. In this case, that hole exists at x equals -1 in the graph. But everywhere else, look at that, I can draw. So what's nice is if we can analyze functions for discontinuity, we can analyze specific x values because everywhere else in the graph except here is continuous. Only at x equals 0 is there a problem there. Only at x equals 0 is there a problem here. And in this case, only at this one little hole, when x equals -1, is there a problem. So that's what we're going to do, is we're going to analyze the graphs at specific x values, but we should be able to know just by looking at the graphs what's going on. So when we do this, what we're going to look at is these three things. Does f of a exist? So in other words, if you plug in a, do you get an output? And if you get an output, good. That's a coordinate. We're going to write it down on the graph, x comma f of a, whatever we get. And what we're going to do here is we're going to look for the limit. Does the limit from the left side equal the limit from the right side? So as I draw from the left and draw from the right, do they touch each other? And that's what we're going to look at. So the order of what we're going to do is we're going to graph first. Because by graphing, I should be able to see whether a specific value creates discontinuity. So I may know what my answer looks like before I start the problem. Then what I'm going to do is I'm going to find f of a. And like I said, if it exists, you're going to write the coordinate a, f of a, just to help you on the graph visually see what's going on. And the third thing we're going to do is we're going to check the limit as x approaches a from the left side. And we're going to check the limit as x approaches a from the right side. We want them to be the same. In other words, as we draw from the graph from the left, and as we draw from the graph on the right, we want to make sure they point to the same value. That's what this part means. Hard to understand in words. While we do it in practice for these examples, it should make sense. So let's look at the first example. So the limit we're going to be looking at for the function, we'll look at just when x equals 3, is it continuous? But we have this entire rational function. So our job is to graph it first. So the first thing I'm going to do is I'm going to find my vertical asymptote. Set the denominator equal to 0. I have a vertical asymptote at x equals 4. So I'm going to graph my dashed vertical line, boom, 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 x equals 4. We are good. The next thing I would do is want to find my horizontal asymptote. And in this case, we're just going to look at our leading coefficients. We have 2x over x. In this case, the x's cancel. So I have a horizontal asymptote at y equals 2. So boom, 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 boom. There's my horizontal asymptote at y equals 2. My next job is to finish graphing. You can use your table of values. You can plug in things. So I'm going to go to my calculator. And notice I already have in here the numerator in parentheses, 2x divided by x minus 4. My calculator is split screen right now. I can see my table of values. 3, -6, 2, -2. I can see I have the right asymptotes. So I'm going to pull up. I have 3, -6. I have 2, -2. I believe we also have a 0, 0. And I can mark those as well based off what my calculator says on the other side. And there's the curve that we had in the calculator. And there's the curve we have. So we have a rational function graphed. We're approaching the asymptotes. We are good. Now, if I were to just examine this graph, forget about the whole idea of what we're looking at. Where is the only point I have to lift my pen? And the only place I have to lift up my pen is right here. When I was graphing, I could graph everywhere without lifting up my pen except at x equals 4. That was the only place where I had a problem with drawing. And that's important to know when checking for continuity at a specific value. Because right now, I don't want 4, I want x equals 3. So what we're going to do is I can look. And what we're looking at is when x equals 3, which is right here, if I were to zoom in like a magnifying glass on it, is the graph continuous just at this specific point? So can I draw that point without lifting up a pen as I come from the left side and as I come from the right side? And right now, I'm thinking I can because the only problem that we said existed was at this vertical asymptote, which was at 4. Well, this point's at 3. So let's see if my hypothesis is right. This means plug in 3. So I had 2x, so 2 times 3, over x minus 4, so 3 minus 4. So I get 6 over -1, which is -6. And I can take a look and I notice 3, -6. That was this point. I'm going to write it on the graph just to kind of visualize, and trust me, that will help you when you have outputs of fractions. So far, it does have an output when I plug in. It created a point. So far, so good. Now, the next part is check it from the left side. As I draw my graph from the left side, what is the graph pointing at? So as I come from the left side, and let me use a different color. As I come from the left side, and as I approach 3, so I'm at 2, 2.5, 2.75, 2.8, 2.9999999. As I approach 3, what is the graph pointing at? What y value? And it looks like I'm still pointing right at the same coordinate. I'm pointing at -6. And I'm going to do the same thing on this right side. Now, I'm not going to examine this curve because it's not approaching 3 on this side. I'm approaching 4. So I have to jump back down here, and as I come from this side, from the positive direction. So I'm at 4, I'm at 3.999, and I go, boom. I am pointing to the same x coordinate, 3, and same y coordinate, -6. So my output still is -6. Since all 3 are the same, we say it is continuous at x equals 3. And I knew that in the beginning, and that's where the trouble comes in with this stuff. It's new, the language is new. Limits as x approaches 3 from the negative side, x approaches 3 from the positive side. But the key is right here, these two things, graph, input, output. And that's what I tried to talk about in the beginning. Notice I said the only issue I had with sketch is at that vertical asymptote. Every other time, if I go from left to right and I'm sketching my curve based off the points in my table, as I'm sketching the curve, there is no problem until I have to lift up when x equals 4 and draw the other side. So when I drew through 3, there's no issues at all. And that's what this was meant to show you. You can do that. So really, a conclusion I think we can draw is when you have a vertical asymptote, that's where your discontinuity exists. When you have a hole, that's where your discontinuity exists. And so it's kind of a warning for you when you are drawing, you're trying to compare what's going on, makes it easy to know this is where my problem is, not here. 3 was good. Only 4 is where it doesn't exist. So kind of use that as a warning when you're working, that you know what the answer should be before you really do the problem when you're dealing with rationals. So let's do number 2. So in this case, this looks like a transformation setup for me, and I love transformation of rational functions, so we're going to kind of do the same idea. So in this case, my a is 4, my h is -5, and my k is -2. Remember the little hint I gave you guys when we first graph with transformations? H comma k is the intersection of your asymptotes. So -5, -2 is where my asymptotes intersect. So I have a vertical asymptote at x equals -5. And notice that is your h value. And I have a horizontal asymptote at y equals -2. And again, that is your k value. Not bad. Now, you could always plug this in your calculator. You could go to y1, do 4 divided by parentheses x minus 5, close the parentheses, -2. Go right ahead. But we're going to use transformations. That a value of 4 means I can go up 1, 2, 3, 4 to the right 1. From the intersection, I can go right 4, up 1. I can even still get 4 by going right 2, up 2 by multiplying. And I can reflect them over as well to the other side. And so I have my curve. Again, going fast, we already did transformations, and we even said we can use our calculators for table values. I just know the role that a plays. Is it's kind of think about the distance up and to the right, up 4, right 1, right 4, up 1. I just have to get numbers that multiply with the area that give me 4. So there's my graph. Again, when I was sketching, I was talking, but I was paying attention as well, is the only time I had to raise my pen was right here. That's it. My opinion is if x equals -5, I had to lift my pen up. It can't be continuous there. And look at that. The problem wants to know, is it continuous at x equals -5? Now, my hypothesis is no. I don't think it is, because I had to lift up my pen in order to cross that point. Nothing exists there. That's my vertical asymptote. So good, I have a hypothesis. I have an idea of what my answer should look like before I start the problem. So now my job is to plug in -5. So I have 4 over -5 plus 5 minus 2. Well, that's really 4 over 0 minus 2. Well, you can't divide by 0. So this does not exist, DNE. That should make sense. We call these excluded values when solving rational equations. So my vertical asymptote is there, it can't exist. So now we do this part. Approach -5 on the left-hand side. Again, I'll change colors. So I'm sketching, I'm approaching -5. I'm getting closer and closer and closer and closer and closer. But notice I cannot hit -5. This rational function is curving and curving closer and closer to that vertical asymptote. So really, what y value am I pointing at as this goes down forever? Well, that's -infinity. And then I do the same thing. I want to approach this -5 from the right-hand side. And so I'm coming -1, -2, -3, -4. But again, I can't touch -5. There's a vertical asymptote there. I can't approach it. I have to get closer and closer and closer without actually touching it. So what is this arrow pointing at? It's pointing at infinity. It's going up forever. So do all three match? Are all three the same? And no. So it's discontinuous, which is what I said in the beginning. Because your asymptotes, the vertical asymptotes, play a role when you're dealing with continuous and discontinuous at specific points. Is the only time your graph is going to be discontinuous at a specific point is really if that point has a hole in the graph, or if that point has a jump in the graph, or if that point has a vertical asymptote there. If it doesn't, then it's going to be continuous. So when you graph, when you do these three things, analyze, think first. Don't just go through the rhythm. Graph and make a hypothesis. Find f of a. Look at the point. Go through it.